Thank you for joining us and welcome to our second episode of Spectroscopy in Action. My name is Paula, I'm Marketing Account Lead at Edinburgh Instruments, and today I'll be joined by Maria, our Fluorescence Product Manager, and Tommy, one of our application scientists. They will be discussing the spectroscopy of fluorescence. Today, Maria and Tommy will discuss how to characterize fluorescence probes by spectroscopy, covering absorption, spectral and time-resolved fluorescence, and quantum. They will discuss how to configure your spectrometer and illustrate these concepts with practical measurement demonstrations. At the end, we'll have a Q&A session, so you'll get the chance to ask any questions you might have. Hope you enjoy the webinar, and I'll now pass over to Maria to get started.
Thank you for the introduction, Paula. This is our first webinar on photoluminescence and absorption, and it's going to be the foundation for further educational webinars. For this reason, I'm going to use this presentation to introduce the spectroscopic techniques, including absorption, emission spectra, lifetime, and quantum yield. These techniques are used in a very wide range of applications, but today we're going to focus on a particular one as an example. We will measure fluorescent probes for bioimaging using absorption and photoluminescence, or PL, spectroscopies. We're going to perform all these experiments in the same instrument, the FS5V2 spectrofluorimeter, which is shown here on the right. I'll start with an introduction on fluorescent probes. They are molecules or particles that absorb light of a specific wavelength and then emit fluorescence of a different wavelength, shown here, emission in red. They are used in bioimaging studies to visualize targets such as proteins, antibodies, nucleic acids under a fluorescence microscope. In these microscopy experiments, the sample is first labeled with the fluorescent probe, which is going to bind to a target of interest. The sample is then going to be studied under an epifluorescence microscope, and in the microscope, we illuminate the sample with excitation light of a particular wavelength that the probe is going to absorb, and then the light emitted by the probe is detected at a different wavelength on the microscope. This is going to provide an image showing the distribution of the target at different points in the sample, showing us an image of where the target is in the sample. We have an example here. We can visualize different parts of bovine pulmonary artery endothelial cells by selecting the appropriate dye. In the example, MitoTracker gives red emission to mitochondria, Alexa Fluor gives green emission to the F-actin network in the cells, and DAPI is going to label the nuclei. We can combine all these three images into one to get the full structure of the cells, as is shown on the bottom right image. So what are the ideal features of a bioimaging probe for fluorescent microscopy? First, it must have specificity to the target of interest. High brightness, that means high absorption coefficient and high quantum yield, so we can detect the image more easily. Photostability, that means that it does not degrade after exposure to light. If your probe falls apart after a few seconds of illumination, then it's not a good probe. It must have a large Stokes shift. That means that excitation and emission wavelengths are far apart, so we can discriminate them in the microscope. It must be biocompatible, so it can image live cells without damaging them. And then it should have optimal excitation and emission wavelengths. For example, red or near-infrared emission wavelengths reduce autofluorescence from biological samples. You don't have interference from the tissue there, so they are ideal. UV excitation, on the other hand, can damage tissues, so it's best avoided for these experiments. And the choice of fluorescent probes that you have these days, it keeps growing thanks to more and more research on better probes and more efficient options. A key aspect of this research is characterizing the absorption and fluorescence of these newly developed probes. So you do need to use spectroscopy to understand how they work and optimize them further. Today, we're going to show you how to perform this characterization on perovskite quantum dots. These are promising new materials. They are small semiconducting nanoparticles, and they have many, many applications beyond bioimaging. But when it comes to imaging, they have the advantage of being very photostable, so they don't degrade when you excite them with light. And you can functionalize their surface with ligands that are going to bind to specific targets. And the greatest advantage, and why people are doing so much research into them, is the possibility to tune their excitation and emission wavelengths by changing their size. This is due to the quantum confinement effect. We have a schematic here on the right. I'm only going to talk about it very briefly, about quantum confinement. So on the first column there, we have a bulk semiconductor. And in a bulk semiconductor, there's a very large number of atoms, and the overlap of atomic orbitals creates a continuum which forms the valence and conduction bands. But when we reduce this semiconductor to a nanoscale size, the band gap between valence and conduction bands becomes wider as you make it smaller, and this is known as quantum confinement. Quantum dots are small enough to have their band gap influenced by quantum confinement. And if you can control their size precisely during synthesis, then you can fine-tune the photoluminescence, emission, and absorption wavelengths. So this will give you a variety of quantum dots of different colors with different emission wavelengths. So they're a novel emitter, and that means we need to characterize them with spectroscopy fully before we use them for imaging. So there's a series of techniques that we're going to use. First, the absorption spectrum is going to let us know at which wavelength they absorb, so we can use them for an imaging experiment. The fluorescence emission spectrum is going to tell us at which wavelengths to image their emission. You would use fluorescence lifetime to understand the emission mechanism, so you can then optimize it further, or to use them in fluorescence lifetime imaging experiments. If you understand their lifetime, then you can study them by FLIM, as we abbreviate it. Then the quantum yield, which is abbreviated as PLQY here, is going to determine the brightness of the probe, which is a key parameter in bioimaging. You need, as I mentioned earlier, you need bright probes to obtain a good fluorescence microscopy image. It would be fantastic to do all these experiments in a single spectrometer. So you save time, you minimize error. And as you're going to see on the next slide, this is possible if you have a dual fluorescence and absorption instrument. And this is indeed what we've used for these experiments. We have carried them out in an FS5V2 spectrofluorimeter. This is the latest version of our benchtop spectrofluorimeter, the FS5. And here you can do absorption and photoluminescence, and you can also do advanced measurements like fluorescence lifetime, quantum yield, near-infrared detection, but you keep a benchtop footprint, which is very convenient for busy labs. It also has plug-and-play sample modules, which you will see later, that are very easy to use. Just a quick tour of what's inside the FS5 and what the main options are. It features a xenon lamp for excitation. This gives you a continuous white spectrum from the UV up to near infrared. You select the emission wavelength using the excitation monochromator, and it then reaches the sample module here, which is exchangeable. After the sample, you have two detection paths. There is a transmission detector at 180 degrees from the sample to measure absorption. And then there is a fluorescence light path at 90 degrees. The fluorescence light is, the wavelength is selected on the emission monochromator, and then it reaches the detector. You can configure up to 2 detectors. You can also configure the FS5 with pulse source for lifetime measurements or a CW laser as well. And it has a range of sample modules and 2 detector ports, so it's very configurable, very user-friendly. We're going to see some of this option later. Let's see now, let's get on to practical matters, and let's see how to measure an absorption spectrum in the FS5. The measurement is going to involve, you have the light source there, which gives you a white light spectrum, and the measurement involves scanning the source's wavelength using the excitation monochromator. So there's a grating that moves and selects the wavelength. So we have monochromatic light passing through the sample and reaching the transmission detector. And as you scan the excitation monochromator, you're going to get a spectrum. So if you measure transmission through a sample and through a blank, you can then use this information to obtain the absorption spectrum of the sample, applying this well-known absorbance formula. In the FS5, I mentioned that it's got two different paths for emission and absorption, although it's primarily a spectrofluorimeter. But the absorption detector is included as standard. So here you have a close-up of the sample showing both light paths, which the absorption at 180 degrees from excitation, and fluorescence is analyzed at 90 degrees from it. The FS5 has a single beam configuration, which means that you have to measure the blank and the sample sequentially. So you can exchange the cuvettes manually, one after the other, or you can use this SCO6 dual cuvette module on the right-hand side, which you're going to see in a video, and it performs this measurement automatically. So coming up next, we have a recording of a live measurement in real time. This was done by Tommy. So Tommy is now going to talk over it and explain how this works over the recording of the measurement. So I'm just going to hand over to you, Tommy, and I'll start the video.
Thank you, Maria. So in this experiment, I used two cuvettes. One was a solution of perovskite quantum dots, and the other was the pure cyclohexene solvent. So I start by putting both cuvettes into the SCO6 sample module. So to then measure absorbance, we then start by setting the desired excitation bandwidth in the signal rate window of our software fluoricle. So once I'm happy with that, I can then go to the absorption scan setup and set the spectral range of interest. So first, the transmission through the solvent-only cuvette is measured, and the current excitation wavelength and signal on the transmission detector are shown on the lower status bar. So yeah, once we've got the transmission detector, transmission spectrum of the solvent-only one, the perovskite quantum dot sample is moved into position, and then it will measure through the transmission through this sample also. And the absorption spectrum is updated live on the screen.
Okay, so I see that it gives you directly the absorption spectrum without having to do any manual calculation. I've just got this screenshot of the video here on the next slide to show people what it looks. Just one question for you, Tommy. What's a good absorption value for these samples?
So if you're wanting to measure fluorescence, like we will do shortly, and you have a path length of your cuvette of 10 millimeters, you ideally want an absorbance value of about 0.1 at the excitation wavelength. And this is to avoid the inner filter effect. So for, I would choose an excitation wavelength between 450 and 500 nanometers in this case.
Okay, thanks, Tommy. Yeah, I can see that's an all right value there. You don't want to go all the way down to 300 nanometers. That would not be practical. So I'm now going to move on, go back to presentation slides, and I'm going to show the next part of characterization, which is fluorescence measurements. So now we have the absorption spectrum of the quantum dots. We want to characterize their emission spectrum. This measurement is going to employ, again, the xenon lamp. And in this case, we're going to fix the excitation monochromator at one wavelength. In this case, as Tommy said, it's going to be between 450 to 500 nanometers. And then we scan the emission monochromator to record the intensity at each wavelength of emission. And this is going to generate a fluorescence spectrum, as shown here, intensity against wavelength. In the FS5, we have a photon counting photomultiplier tube, which means that you can measure very weak photoluminescence signals. That means we can study very challenging samples that have low brightness. And now I'm going to hand over to Tommy again, so he's going to show us how this happens in the FS5E2 software.
Thanks, Maria. So when we want to measure the photoluminescence spectrum, we initially go back to the signal rate window and we'll set the desired excitation and emission bandwidths. Once we've done that, we'll set the sample position to 2 because this is the position of the quantum dot cuvette inside the SCO6. I'm now going to increase the emission bandwidth to get around 1 million counts per second on the emission detector. And this is to ensure that we get good signal to noise in our spectrum. So once we've done that, we can then go to lambda, and then in the emission scan setup window, we can then set the desired scan parameters. And this will show you the emission spectrum updated live in the software. So now it's been acquired, we can see that our quantum dots have a narrow emission centered around 525 nanometers. And then I've just joined the absorption and the emission spectra together to more easily compare them and normalize them as well to their peak value.
Thanks, Tommy. I can see, so I can see this looks a lot like quantum dot spectrum to me. Do you have any comments about these spectra? What can you find? What can you infer from them? Okay, thanks, Tommy. Let's see what else we can study about this sample. The next step is going to be photoluminescence lifetime of the quantum dots. So photoluminescence, I'm going to be referring to as PL decay. It's going to provide the dynamics of the recombination processes that happen inside the quantum dots. And these are a complex mix of radiative and non-radiative relaxation pathways after you excite. And it's important for researchers to understand these processes so they can optimize further the efficiency of these probes. As I mentioned in one of the first slides, you might also want to characterize the lifetime if you're going to use them for imaging experiments like FLIM or PLIM microscopy. So the definition of PL lifetime is shown here on the left. It corresponds to the average lifetime that a molecule spends in the excited state before returning to the ground state. And you determine it by measuring PL intensity as a function of time. And the lifetime, which is the tau in the equation, is obtained from an exponential fit to that equation there. The most accurate technique to measure PL lifetime is time-correlated single photon counting, or TCSPC. TCSPC is going to register each individual pulse from an excitation laser as a start electrical pulse, and each individual photon emitted by the sample as a stop electrical pulse. And besides registering these pulses, it also records the time difference between start and stop. So this is T in the schematic there. And it builds a histogram in the electronics photon by photon that is then transferred to the software so you can do your lifetime fit. This technique is very, very sensitive and accurate. So you can obtain a fluorescence lifetime decay with a resolution of picoseconds, provided you have fast enough sources and detectors. You can equip the FS5E2 with a TCSPC upgrade so you can measure PL lifetimes from nanoseconds or even hundreds of picoseconds. That means that we can characterize the PL lifetime of our perovskite quantum dots in the same fluorometer instead of setting up a different instrument. There is a laser port on the side of the instrument, and as you can see on the video there, swapping lasers only takes a few seconds. I'm going to hand over to Tommy again, who's going to show you how to perform a TCSPC lifetime in the FS5E2. Over to you again, Tommy.
Great. So when we want to measure a PL decay, we first go back to the signal rate window, and we're going to change the excitation source to be the TCSPC laser. So the laser is mounted on the front of the FS5, and there's an intensity filter to control the power. So here I'm just adjusting this neutral density filter so the emission count rate is less than 5% of the pulse repetition rate, which in this case is below 50,000 counts per second. So once I'm happy with that, I then go to tau and then manual, which brings up the lifetime measurement setup window. So once I'm happy with my parameters, I can then start the decay. So here, the photoluminescence decay is recorded photon by photon using time-correlated single photon counting. The current progress is shown in the lower left. So once our decay has been acquired, we can then fit it to obtain the lifetime. So for this sample, I'm using a 4-component exponential model to fit this decay. And we can see that it has an intensity-weighted average lifetime of around 16 nanoseconds, which is that sort of red flashing parameter on the screen there.
Okay, I'll just leave it there in that frame. So how can you tell if you have a good fit?
So first, by looking at the residuals curve, which is a green line underneath the decay, and you can see that it's a random distribution about the baseline. And we can also look at the chi-squared parameter, which is a indicator of how well the data has been fit. So chi-squared between 1.0 and 1.3 is generally considered a good fit.
Yeah, I see you had 1.28 there, so it's good enough. Thanks, Tommy. I will now move on to the final step in our characterization, which is going to be the quantum yield of the dots. Quantum yield, also abbreviated as QI or PLQI, is defined as the number of photons emitted over the number of photons absorbed by the sample. And to measure it accurately, we're going to use an integrating sphere, which is going to provide the absolute number of photons absorbed and emitted. The sphere, shown as schematic on the right, has a reflective inner surface, which is going to average out any spatial effects and is going to redirect any diffuse light to the output, which has a baffle there, so you don't have any direct reflections. The sphere makes it possible to compare light emitted from different samples quantitatively. To measure the absolute quantum yield, we're going to scan the absorption and emission ranges of the sample and of a non-absorbing reference. In this case, it will be a solvent blank. In the plot on the left-hand side, the sample spectrum is purple and the reference is green. The absorption emission areas of this sample are then of each sample, the sample and reference are integrated, and the difference between the sample and blank is going to be used to calculate the number of photons absorbed or emitted, which make up the quantum yield formula above. So in the equation, S stands for scattering, which means the absorption band, and E stands for the emission range of the sample. And they are shown in the spectrum there. In the FS5E2, quantum yield measurements are going to be performed in the SC30 sample module. This is a plug-and-play sample module that incorporates an integrating sphere inside it, and this sphere has a drawer, so you can put both cuvettes and solid samples in there. I think it's easier to see it in the video, so I'm just going to move on to the next and final video where Tom is going to show how to use the SC30 to measure the quantum yield of our perovskite quantum dot.
Great. So to measure quantum yield, we first have to switch off the laser, and we're just going to remove both of the cuvettes from the SC06. Once we've done that, we can then take the sample module out using the quick release button. So this is one of the great advantages of using the FS5 is that these sample modules can be easily swapped out for different applications. So the SC30 integrating sphere slides into the FS5 and locks into place. The Fluorico software will automatically recognize that a new module has been installed. So first of all, for the quantum yield measurements, we're going to change the light path, the excitation source, back to the xenon lamp and set the detector light path to the integrating sphere. So we're going to measure the solvent first, and so we're going to pull out the drawer and place in the cyclohexane cuvette. Once we've done that, we can then set the excitation and emission wavelengths both to the desired excitation wavelength, which in this case is 475 nanometers. We then adjust the excitation and emission bandwidth to then give around 1 million counts per second at the excitation peak. So this ensures that the detector will be operating in its linear regime throughout the quantum yield measurements. Once we've done that, we can then set the scan parameters in the emission scan setup window and run the measurement as a normal emission scan.
How did you decide on the wavelength range for this quantum yield measurement?
So for the quantum yield measurement, you want to capture both the scattering excitation peak and the emission peak. So I set the wavelength to be 10 nanometers, 10 to 20 nanometers lower than the excitation wavelength. So it's a good idea to check the emission spectrum previously and to set the end wavelength so that it covers the entire spectrum.
Okay.
So in this measurement, the peak at 475 nanometers is the scattered excitation light. And since this cuvette contains only cyclohexane, there are no other peaks present in the spectrum. So after the spectrum has been acquired, we can then replace the solvent cuvette with the sample cuvette containing the quantum dots. And once we've loaded in our sample, the emission scan is then repeated with the exact same parameters using the rerun button on Fluorico. So again, we're going to see the scattered excitation light at 475 nanometers. And then we're also going to see now a small photoluminescence emission around 525 nanometers. It's quite difficult to see on this scale. This is a linear scale, as the scattering peak is a lot more intense. Though when we put it into a logarithmic scale, it'll be much more easy to see. So now that we have both measurements for the blank and the sample, we can then combine them into one window using the join function. And then we can then open the quantum yield analysis wizard. So after choosing that our sample is a liquid and we did a direct measurement only, the wizard will automatically assign the reference and sample spectra, and it will select the wavelength range of the scattering peak. So it's just left for the user to then define the emission range with the cursor, and then we can then press calculate. And we can see that the quantum yield of the dots is calculated to be just over 5%.
Okay, thank you, Tommy. I leave that quantum yield result there, and that concludes our characterization study, as well as today's webinar. So I'll just jump onto a conclusion slide. We have shown, I hope, how to use the FS5V2 to comprehensively characterize fluorescence probes for bioimaging applications. This includes absorption, fluorescence spectra, lifetime, and quantum yield. I hope this was useful for everyone watching. And I just wanted to highlight that performing all this technique on a single instrument is going to offer many advantages. I hope I've been able to show you can screen many samples in a short period of time, and this is going to accelerate the development of new fluorescent probes. That concludes our presentation today. Thank you everyone for watching. I hope this was useful, and I'll be happy to answer any questions now.
Thank you, Maria and Tommy. That was really interesting and insightful. So yeah, as Maria said, the question box now open. So if anyone has any questions they would like answered, now's your chance. We've had one question already, which is, are there any limitations to using perovskite quantum dots for bioimaging compared to more traditional fluorescent dyes?
Yes, so I'm speaking as more of an expert on the instrumentation and not on these samples in particular, but we've measured them, we've done a bit of reading, we discussed with customers who are working on these projects. And one thing that people mention in publications quite a lot, there's a couple of things. So that one of the main concerns is biocompatibility. These quantum dots are made of sometimes toxic materials, and the biocompatibility has not been established yet. So that's a caveat I have to add for these things. They're useful for a lot of things. Bioimaging is a research area. And another thing would be synthesizing them easily and consistently in terms of size and functionalization. I believe this is also a bit of an issue and an area of work.
Okay, thank you, Maria. Why did you choose 4 exponential decay to fit the lifetime?
Okay, so there's an easy way to tell if a decay is multi-exponential, because the software plots it on a log scale. So if it's a straight line, you know it's a single exponential. But in this case, for these quantum dots, in particular for these materials, you have a very complex mix of radiative and non-radiative relaxation processes. And also you have a distribution of quantum dots, each with a slightly different lifetime. So we find that 3 or 4 exponentials provide a good fit.
Mm-hmm.
For perovskites in particular, people tend to use stretch exponentials as well, at least I know for the bulk materials. And this is something that you can do with an advanced fitting package that we have in Edinburgh Instruments. It's called FAST, and we have a few application notes that demonstrate how the stretch exponential fit work. So that's also another option you might want to look into.
Thank you. Also, how does temperature affect the photoluminescence of perovskite dots? Can the fluorimeter control sample temperature?
Okay, so again, not something we've done for these particular samples. But in general, temperature is going to affect photoluminescence significantly for these materials. For semiconductors, you're going to have, as you increase the temperature, the lattice is going to expand, and that's going to possibly shift the peak. You can sometimes tell phase transitions by looking at the shift of the peak, and we have a few publications on this. Also, the quantum yield changes with temperature quite a lot. In general, if you decrease the temperature, the quantum yield of photoluminescence increases. That's the general rule, because you're switching off non-radiative decays. And in terms of controlling the temperature, the answer is absolutely yes. We have several options in the FS5. There are cassettes for controlling the temperature in a cuvette up to 100 and something degrees, 150. And we also have options for liquid nitrogen temperature control, like putting a cryostat into a sample module. And it's all software control, so you can do maps of spectra or lifetime with temperatures.
That's great, thank you. I think that's all the questions that we have today. So I think we'll just end there. So thank you very much, Maria and Tommy, for explaining the spectroscopy of fluorescent probes to us. This webinar will be published on YouTube for you to watch again and share with any of your colleagues who you think might find it useful. We'll also be continuing this series, so please do make sure you're subscribed to our newsletter and be the first to find out about it. And also, if you subscribe to our YouTube channel, you'll get all the latest videos. Finally, thank you very much for joining us. We hope you enjoyed this session and found it useful. We will see you next time.